Okay, so this is a very quick checkpoint. So now we have three charges. So we have two photons. P, these two P is photons. So you know that it has a positive charge, and one electron here on the same axis. So on the central photon, what is the direction of the force due to the electron? So what is the direction? Pointing to the left. Yeah, left. Very, very stupid. Very stupid. I think you should have known it in high school. So what is the force due to the other photons? Pointing to the left. So what is the net force? Left. Okay. So very easy. Any question regarding to this one? I suppose very easy. So we have sample problems. So of course, for physics class, you need to calculate something, some numbers. Actually, in the exam, all the stuff are calculations. I do not ask you to fill in the blanks to memorize some scientist name. It doesn't make sense. So actually, you still need to calculate something in the quiz or exams. So for this one, so figure A shows two positive charge particle fixed in place on x-axis. The charge are Q1, Q2, Q1, Q2 here and here. So they are separate by r equals to 0.02 meter or 20 centimeters. So actually you need to care about the units, meter, centimeter, this or millimeters. You need to be careful during the quiz or exam. Actually, I forgot a C here. C here. So what is the magnitude and direction of the electrostatic force on particle 1 from particle 2? So it is very easy. Just substitute all the numbers into the Coulomb's law, then you get so you substitute the number or just use K times Q1 Q2 R square, and then you just substitute the number. K is 8.99 times 10 to the 9th, and then Q1 is 1.6 times 10 to minus 9, and then Q2 is 3.2 times 10 to minus 19, 10 to minus 19. So R is 0.02 quantity square. So the answer will be 1.15 times 10 to minus 24 Newton. So actually, during the intermediate stage, I suggest you usually write the formula first, and then you substitute the number, and then you write the answer. Oh, actually, during I grading the quiz or exam in the past, some usually I will see that you just write it and then you write the answer, and then if you are correct, that's still okay. But if you are not correct, then you also lose the point for this part. It is somehow that if you can write more, then you can then even if you calculate the final answer incorrectly, then I can still give you intermediate step points. And actually, you don't really need to write the SI unit for the intermediate step. If you can write the correct SI unit for the answer, I think it is already good enough. I think it's already good enough. So if you want to write it in a vector form, it will be somehow like this. It is equals to 1.15 times 10 to minus 24 Newton, negative I, negative I. Yeah, because suppose x direction is pointing to the right. So in the textbook and also the solution, we'll usually use I hat for the x unit vector on x direction, j hat for the y direction, k for the z direction. For the z direction. So we'll use ijk. And actually, F12 is minus, F12 point to the left side, so it is a negative here, I. Any questions? No questions. Very simple. Yeah. So for the next case, figure C is identical to the previous one, except particle 3 is now lying on the x-axis between particle 1 and 2. Particle 3 here has a charge Q3 equals to blah blah blah. Oh, I also miss a C here. So at the distance 3r/4 from particle 1, what is the net electrostatic force on particle 1 due to particle 2 and 3? So just now we already know that F12, so that we can also calculate F13. Yeah. So F13 is nothing but K Q1 Q3 over 3r/4 square. So it is 8.99 times 10 to 9, and then Q1 is 1.6 times 10 to minus 19, and Q3 is actually you can do it in two different ways. You can just calculate the absolute value, and then you determine the direction by yourself, because you know that Q1 is positive, Q3 is negative, so that you know that they should attract each other. So you know that F13 points to the right side, f13 points to the y side, or you can just keep all the signs, so you know that this is positive, this is negative, so that you will get a negative, uh, negative answer. So for Q1, our head is somehow like this, which is actually minus I hat. So if you use, you can also always believe on the math, what you calculate, or you can use another way. You determine the direction by yourself. It is also okay. It is up to you. But actually, during the quiz or exam, you can do it both to double check what you really think is correct or not. So 3/4 times 0.02 quantity square. So we know that f, sorry. So we know that it is actually 2.05 times 10 to minus 24 Newton. Or you can write it as F13 equals to 2.05 times 10 to minus 24 and I had F13. So actually, F so actually F1 net is F12 plus F13. Actually, you can just substitute the number minus 1.15 times 10 to minus 24 plus 2.05 times 10 to minus 24. So the answer will be 9 times 10 to minus 25 Newton in the positive direction. F13 is slightly, the magnitude of F13 is slightly larger than F12. So this is F1 net. Any questions? Okay. So for the next case, E is identical to the previous one except particle 4 to the very previous one. Except particle 4. Particle 4 is a negative charge, which has a charge amount of minus 3.2 times 10 to minus 19 at the distance 3r/4 from particle 1 and lies on the line that makes an angle theta equals 60 degrees with the x-axis. So theta equals 60 degrees. So what is the net electrostatic force on particle 1 due to particle 2 and 4? So now we just remove Q3. So we only have 2 charges. So still we need F12. Actually, I think this is very easy, but you really need some effort to get the answer only. So actually, F14. So F14 is K times Q1, Q4. Take the absolute value, and then this is the same 3r/4 squared. And then you substitute the number 8.99 times 10 to 9, and then this one 1.6 times 10 to minus 19, This one 3.2 is times 10 to the minus 19, and then this one 0.002, and then you substitute, and then you get the answer. So this is actually the same as the previous one, which is 2.05 times 10 to minus 24 Newton. But this is different from the previous case. Now F14 should be equals to 2.05 times 10 to minus 24 times cosine 60 degree. Cosine 60 degree Newton I. Because this is F14. So you have this one. This one should be F14 cosine F14 cosine 60 degree, and this one should be F14 sine 60 degree. So in the x-axis should be 2.05 times 10 to minus 24 times cosine 60 degree plus also F14 and sine 60 degree and J hat. Actually, you can just press the calculator to get this number. And then finally, you can calculate F1 net is, you add them together. This one is minus 1.15 plus this number. So it will be nothing but minus 1.25 times 10 to minus 25 Newton I hat, and then plus 1.78 or times 10 to minus 24 Newton J. So the calculation should be very simple. The only math involved is the cosine 60 degree and sine 60 degree. Any questions? Very easy, right? So for the next one, figure A shows two particles in a place. A particle of charge Q1 is AQ, and Q2 is negative 2Q at x equals L. At x equals L. At what point other than infinite far away can a proton be placed so that it is in equilibrium? Equilibrium means no net force acting on it. The net force on it is 0. So is that equilibrium stable or unstable? Actually, this concept is a bit more difficult. You may learn more about that in control theory, somehow like that. But at this point, I just try to explain it to you. So now we have two charges here. One is positive, one is negative. We try to place a charge somehow on this axis. If it is not on this axis, then you suppose that you will go away. You go away. It must be on this x-axis so that the net force is 0. Because if one charge is here, one charge is there, and then you place it there, then the force is somehow like this and this, they can never add to be 0. So it must be on the x-axis, right? So there are 3 cases. The first case is I put a positive charge in between, or I put it on the left side, or I put it on the right side. So for the first case, if I put it in the middle, so you know that this is positive, Q1 is positive, Q2 is positive. So that they repel each other, which means that F1 points to the right side. F1 points to the right side because these two repel each other. And this one is positive, this one is negative, so that they will attract each other. They will attract each other, so that F2 points to the right side also. So F1 and F2 both point to the right side, they cannot add to be 0, so that this case is rejected. For the second case, if we put it on the left side, so we know that this is positive, Q1 is positive, this is positive also, so that they repel each other, which means that F1 points to the left side. And this case, Q2 points to the negative, Q2 is negative, this is positive, so that they attract each other. So F2 points to the right side. Then you ask whether or not it is possible that they add up to be 0. The answer is no, because Q1 is larger. So that actually Q1, the absolute amount of Q1 is 4 times larger than Q2, which means that F1 is always larger than F2. F1 is always larger than F2 because it not only closer means larger force, and actually the amount of the charge is also larger, so that F1 is always larger than F2. They can't add up to be 0. So we also reject these cases. And for the third case, we place it to the right side. Now this one is big, this one is small, but this two is closer to these two, so that they may have a balance between them, so that at some point, and then F1 and F2 add up to be 0. So we try to accept the third case, and then we try to find the point so that the net force acting on this charge is 0. Okay. So F1 net is F1 net is nothing but no, sorry. We can just write it like this. We can just write F1 is the magnitude of F1 is equals to F2, because we have argued that they should have a negative direction. So as long as they have a equal amount of magnitude, then they will cancel each other perfectly. So F1, we know that this is L, So and let us assume this is x, which is the distance between Q2 and R. So that the force Q1 is actually no, not this one is x. This one is x. Actually, the x coordinate of this one is x. so that we can have K times 8Q, 8Q, which is Q1, and then the charge, we don't know actually the amount, so we call it QP, and then the distance between Q1 and R is X, so X squared. And then F2 is nothing but K, and then this one Q2 is negative 2Q, so we use the absolute value 2Q, and then QP we also don't know, but you can see that they will cancel each other. So we don't really need to know what QP is. And the distance between Q2 and R is X minus L squared, because the whole one is X, this one is L. So this one is X minus L. This is X minus L. So we can further make some cancellation. K and K can be cancelled. Q and Q can be cancelled. So that is just have a so we can multiply 8 by this X minus L square, and then we multiply 2 by X square, and then they're the same. So it's just some algebraic calculation, so that you can know that 3x squared minus 8xl plus 4l squared equals to 0. So this is a quadratic equation with one unknown, so that you can calculate that x equals to 3 over 2l or 2l or 2l. We have two answers, but one of it will be rejected. Actually, this one will be rejected. Why? Because if x is 2/3 times L, which means that it is somehow like here. X equals 2/3 times L, which means that it is in between Q1 and Q2, which is not correct, because it means that this X minus L is negative. So we'll reject this one. And the remaining answer is this: x equals 2L. Actually, this one is unstable. I'm not sure if I have enough time to. Maybe I can just finish this explanation. So you can imagine somehow like this. Actually, the F net is nothing but K times 8Q QP over X squared minus K times 2Q QP over X minus somehow like this, because just now we have the first term equals the second term. Now we just minus them, and then it is actually the magnitude of the net force acting on that charge. Now you can just factor it out. You have also 2Q QP, and then you will have 4x squared minus 1 over x plus L. Okay, should be simple. I just factor the common factor out. So now we know that when x equals to 2L, when x equals to 2L, then we know that F net is 0. F net is 0, right? We just make this calculation in the last slide. So so now suppose if you put x equals to 2L plus delta L, you move it a little bit to the right side. You move it to the little bit to the right side. You can find that this one is positive. This one is positive. Somehow like this. It will be somehow like 2L plus delta L square minus 1 over 2L plus delta L minus L square. It would be somehow like 1 over L square plus L delta L plus delta L square over 4, and then minus 1 over L square plus 2 delta L 2L delta L plus delta L square, which will be always positive, Then I'll say that it is unstable. It is unstable. What does it mean? What does it mean? Yeah. That's the point. This is what we call the positive feedback. The positive feedback. It's not easy student to handle in control theory or anything. Which means that if a point is placing here, if I just at this point perfectly, you will have a 0 net force, then you will not move according to the Newton's law of motion. But if it is moved a little bit to L plus 2L plus delta L, then the force will be positive. The force will be positive. Then it will go away soon. It will go away soon. It's just like if you have a curvature, something like this, and then you have a ball here. So that this is stable. If you just move it to the left side, it will go back. If you just move it to the right side, it will go back. But now it's somehow like this. You place it here, you place it here. And then you just push it a little bit or just throw it a little bit, and you go away, or go away like this. So this is what we call unstable. This is somehow unstable. You can imagine it in a slightly layman way like this. So actually the charge is quantized. It's very trivial. The unit charge is 1.602 times 10 to minus 19 Coulomb, which is nothing special. You cannot have a 0.5 charge, somehow like this. I don't think I will go for it, and the charge is conserved. It is quite trivial. Maybe I can talk a little bit more in the next tomorrow.